So this is a video on network solids, which I already talked about identifying. I'm just going to discuss briefly their properties. Now, a network solid you want to think of as being like a huge monster-sized molecule. So a single diamond, right, you can think of as one big molecule that you can hold in your hands, okay? And every single carbon atom is essentially bonded to every other carbon. So this is a picture of the network solid that we call diamond, showing, maybe 12 atoms, okay? Each carbon, is the carbon I'm drawing in here, is surrounded by one, two, three, four other carbons in a tetrahedral arrangement, all right? These are all single bonds, so they're all sigma bonds. I'm only mentioning this because this affects the properties of the substance. So because all the atoms are connected by covalent bonds, okay, that makes network solids, they are very hard. If you look at Mohs hardness scale, you have diamonds at the top and silicon dioxide, which is another network, which is quartz, is the second hardest. So this diamonds are a 10 on the Mohs hardness scale, and silicon dioxide is a 9. Okay, they have very high melting points. They have the highest melting points. Below them will be metallic substances and ionic substances. Ionic substances tend to have higher melting points than metallic substances, but obviously there's some overlap there, okay, within that region. So certain metals will have melting points that are higher than certain ionic compounds if the lattice energy is very weak, all right? There is overlap, but the general rule is networks are the highest melting points, followed by ionics, followed by metals, okay? Number three, they tend to be insoluble. So if you throw a quartz rock into the ocean, it's not going to dissolve, nor will a diamond or a pencil lead, which is graphite. All right. Number four, all right, has to do with conductivity. The conductivity requires mobile electrons. All right. And we're talking about really electricity here, not so much heat, although I think for the most part, these guys are poor conductors of heat as well. But I'm not even seeing anything on it specifically in Wikipedia, so I'm not going to think that you're going to need to know that specifically. In terms of electrical conductivity, okay, many of them are poor conductors. For example, diamonds are poor conductors, okay? Silicon dioxide, quartz is a poor conductor, it's an insulator. However, some of them do conduct. The classic example of this is graphite. And graphite doesn't have exactly the same qualities of a diamond, right? If you look at graphite, the reason why you can write with a pencil lead, which is what graphite is because the carbons are bonded covalently in these layers, okay? Now, within the layers, all the bonds are sigma bonds, all right? But between the layers, in this area that I'm darkening in right now, are overlapping p orbitals, which means these are pi bonds in here. And the pi bonds are said to be delocalized. And what that means is the electrons don't have a specific location, which means the electrons can move, which means it can conduct. Also, pi bonds tend to be weaker. So this is why, okay, you can write with a pencil because the pi bonds are easily broken, whereas the sigma bonds, which are the bonds that I've written in here all throughout the diamond, are very difficult to break. So you can not only can electrons flow through those delocalized pi bonds, okay, and the overlapping p orbitals, but you could easily, just remove, like you could just take this right here, this layer of graphite, and it'll just come right off it with a little bit of effort on your part, and you would be writing with your pencil, okay? And when you're writing with your pencil, you're breaking those pi bonds, okay? Okay, and so while we say these are the hardest substances, obviously, okay, some of these guys can cleave along certain planes, particularly where the pi bonds are located. Okay, there are other networks. The general rule that I've seen in the AP is they're looking for these guys right here. Okay, so silicon dioxide, which is just quartz, okay, and is found in all ceramics, basically. All right, silicon as an element forms a network. Germanium does too, and some of these guys are what we call semiconductors. What that means is, as it is, they do not conduct, but if you apply a certain voltage or potential, you can get those electrons to move in what's called a conduction band, but you need to apply a certain specific voltage for it to happen. Because you have to apply that voltage, they can act as a switch, and they're using semiconductor chips. And they often dope the chips as well to create what's called holes. I'm not going to get into this semiconductor technology, okay? But you should maybe know that they do exist, okay? And while they're not considered good conductors, they're considered semiconductors, which means they can conduct under certain conditions when you apply a voltage. All right, and often they dope them. Now, there's lots of other networks. You don't need to know these ones. I would definitely know diamonds, graphite, silicon dioxide, silicon, and germanium. Okay, there's lots of other ones though that tend to involve elements around group 14 with 4 valence electrons, which means they can make 4 bonds. So aluminum will form a network with nitrogen, aluminum nitride. I can't see them giving that to you on the AP exam because you might think it's ionic. And, unless you're being told it's a very hard substance, it doesn't conduct, it doesn't dissolve in water, then maybe you'd be like, oh, it's a network, not this, right? They have to give you information. Okay. Boron nitride is another one. Okay. But there's even weird ones like ReB2. I have no idea what this is. I barely know where Re is located on the periodic table, but I'm on Google, and according to this rhenium diboride is a network solid. So I know this substance has a high melting point, probably does not conduct, it's insoluble in water, etc. Okay. Julia is working on gallium arsenide. Okay. It's used in semiconductors. It's got special properties that make it an interesting semiconductor, particularly at high temperatures. It's another network. Okay, note, they're not using those columns, they're like around it. All right. Do you need to know this? I'm not sure. Anyway, I hope this helps. It's probably longer than it even has to be. My assumption is there's not a lot they can ask you on this.